6.2, solutions about an ordinary point. Well, I guess that's fine. So we define basically here a second order linear differential equation. We've been looking at this for a while. If you divide everything through by that a sub 2 of x, then we have equation number 2, y double prime plus p of x, y prime plus q of x times y is equal to 0. We want to examine the nature of a sub 2 of x. Examine the nature of a sub 2 of x. What we're going to do is just basically set a sub 2 of x equal to 0 and solve for x. Here, if the values that we call, when we do that, we call them x naught, a point x is equal to x naught is said to be an ordinary point of the differential of the differential equation. That's funny. If number one, that first equation, if both coefficients p of x and q of x in the standard form of equation 2 are said to be analytic, that is, for a function to be analytic at a particular point, we say that that function is well defined. Actually, you can actually write a power series based on that particular function, which is the very sophisticated terminology for saying something is analytic. I think simply saying that a function is analytic if when you evaluate the function at x sub naught, you get something that's defined. You don't get like 1 divided by 0, in just very simple terms. So the function said to be defined at that particular point. We have something very easy to look at to determine that. If that's not the case, then x sub naught is said to be a singular point. So let me scroll down and just show you the difference, and then we'll move on. Today, just based on the header of this section, solutions about ordinary points. So we can determine that a particular value x naught is an ordinary point, then we have a theorem that tells us that we should be able to find so many solutions if we evaluate the differential equation about a so-called ordinary point. So here a number x equal to x naught is said to be ordinary if when you evaluate a sub 2 at x naught and you don't get 0, or this guy is not equal to 0, then we say that here the x naught is said to be okay, that's a comma there. I thought something was going crazy. X equal to x naught is an ordinary point if a sub 2 evaluated at x naught is not equal to 0. Well, if a sub 2 of x naught is equal to 0, then we call x naught a singular point. So singular, if you remember something about a matrix, say that a matrix, if it does not have an inverse, is said to be singular. And that's somewhat the idea here, that if I get a value for x naught that makes a sub 2 equal to 0, then we call that particular function evaluated at x naught, we call x naught a singular point. Just for example, see this example here, x squared minus 1 times y double prime plus 2x y prime plus 6y equal to 0. Well, a sub 2 is this x squared minus 1. That's a sub 2. So if we set a sub 2 equal to 0 and then solve for x, here if I solve for x, I get x equal to plus or minus 1. We say that x equal to 1, x equal to minus 1 are singular points, because that gives me 0 for a sub 2. Think about it. From equation 1 to equation 2, you want to divide everything by the a sub 2. So you get y double prime plus p of x, y prime plus q of x times y equal to 0. Well, if a sub 2 is 0, then you'll be dividing by 0. And so you get singulars. And singular means that's not defined. So you want to x out all of those points that are called singular. So if x is an ordinary point, say for example, look at this problem again. x equal to plus or minus 1 is said to be singular points. That is that I get 0 for a sub 2 if I plug in x equal 1. Right? I get 1 squared minus 1, that's 0. That's a sub 2. If x is equal to negative 1, I get negative 1 squared, which is 1 minus 1. I get 0 again. So here, the factor x minus 1, the factor x plus 1, if I divide everything by this equation, by those factors, I get 2x divided by x minus 1 times x plus 1 times y prime, plus 6 divided by x minus 1 times x plus 1. But if x equal to 1, if x equal to negative 1, I'm dividing by 0. That's undefined. All right, so that's the idea, what it means that a function is said not to be analytic at x equal to 0. That the function is not defined at that particular point. So today what we're going to do is determine the values of a sub 2 where I get singular points, but then look at an ordinary point and say, if this x equal to whatever is an ordinary point, there's a theorem that says I ought to have a certain number of solutions from there. So here, x equal to 1, x equal to negative 1 are singular points. All other values are ordinary. So x equal to 3, x equal to 4, x equal to 1/4, x equal to 1/3, those are all ordinary points. I can divide the equation by those values, and I get the resulting equation to be defined. Right? So if x is an ordinary point, then I have a theorem that says that I should be able to find certain solutions. Well, the theorem here says that it's the existence of a power series solution. If x is an ordinary point, then there exists 2 linearly independent solutions in this form. Now here's the cool thing about this form here of the power series centered at x naught. This is the same form from section 6.1, right? Matter of fact, in 6.1, the problems there, that's what you were doing. You were finding the power series solution about an ordinary point. You just didn't say it. So 6.1 and 6.2 are the same. So everything we did in 6.1, we'll do the same thing here in 6.2. So let's take a problem here and solve. The cool thing about this is that when we solve the solution, you're going to get 2 solutions. Wow. Now, why is that interesting and why is that important? Well, you remember in the superposition principle where you had a function, a differential equation of order 2, some y double prime plus and so on, that when you looked for the homogeneous solution or the complementary solution, it was typically y sub c equal to c sub 1 times some solution y sub 1 plus c sub 2 times some y sub 2. Do you remember that? Right? So now we're going to actually build those 2 solutions based on power series. And those are the 2 solutions that they're talking about here, that we can always find 2 linearly independent solutions, c sub 1 times y sub 1 plus c sub 2 times y sub 2. Let's find them. The pattern scheme of the solutions in terms of how we do the steps is the same from 6.1. So let's take, I have numbers 7, 9, and 11. Let's do number 9. It's right in the middle. So we let y equal to the summation as n goes from 0 to infinity of c sub n times x minus, I'm going to put the whole thing in here for right now, x minus x sub naught times x to the n. Now we're trying to examine this about an ordinary point. Well, let's back up. It says for problem 7 to 18, find 2 power series solutions of the given differential equation about the ordinary point x equal to 0. Right. So what does that mean? Let's come back to the problem that we're working. What that means is that x naught is equal to 0 is an ordinary point. Well, if you take a sub 2 from this problem, a sub 2 of x is equal to 1. Right? So this implies that all values here are said to be ordinary. So we pick x naught equal to 0. And they give us that for the problem. So that x naught here is 0, so all we have is c sub n times x to the n. So we pick x equal to x naught. An ordinary point. So thus, y is equal to the summation as n goes from 0 to infinity of c sub n times x I apologize. I'm thinking about section 6.3. This is to the nth power. So here x naught is 0, so I just end up with x to the nth power. So just like before, I'm going to take, I need the first derivative because this problem has the first derivative, and I also need the second derivative because this problem has the second derivative. So y prime is equal to the summation as n goes from 0 to infinity of c sub n times n times x to the n minus 1. Then what about y double prime? The summation is n goes from 0 to infinity of c sub n times n times n minus 1 times x to the n minus 2. So for this problem, it's y double prime minus 2x y prime plus y, that's equal to, so y double prime is the summation double. As n goes from, we're going to take this guy here and plug that in for y double prime, c sub n times n minus 1 times x to the n minus 2. And then this is minus 2x, just from the problem itself, times y prime. This is the summation as n goes from 0 to infinity of c sub n times x to the n minus 1. And then plus the summation as n goes from 0 to infinity of c sub n. This is just y, so that's just times x to the n. Well, that's all equal to 0. Okay. We said before that, notice if for the first summation, if you plug in n to equal to 0, then at that term, at c sub 0, I get c sub 0 times 0. So we can start the count at 1. But then look at n equal to 1. 1 minus 1 will give me 0. So it's safe to start this summation at n equal to 2. Over here, you can start this count at n equal to what? For that second summation. You can start that at n equal to 1 because here I have an n there times everything. So if n is 0, then that guy just goes out to be 0. So I'm going to fix this. We're going to trump this up to n equal to 2 to infinity. N goes from 1 to infinity there. That one stays the same. That x out here, this minus 2 times x, I'm going to put that x on the inside. Now notice that I can do that because the terms that are changing actually is anything that involves here an n. So I couldn't pull out n in front of that summation. This is a summation of n things. But anything else is treated as a constant to the summation of n things. So here I can take this x and I can associate it with x to the n minus 1. So let's do that. So this is the summation as n goes from 2 to infinity, c sub n times n minus 1 times x to the n minus 2 minus 2 times the summation as n goes from 1 to infinity of c sub n times x to the n. Because that x to the first times x to the n minus 1 is just x to the nth power there, plus the summation as n goes from 0 to infinity of c sub n times x to the n. That's equal to 0. So now what we're going to do is we're going to introduce the k factor. Here, let k equal to n minus 2. So k plus 2 is equal to n, and k plus 1 is equal to n minus 1. And over here, let k equal to, I always go by that exponent up there in terms of what k is to equal to. So let k equal to n. Right? So nothing else to do there. And then over here, likewise, let k equal to n. So I'll come down. This is the summation as k goes from, well, if n is starting at 2, we get 2 minus 2. K starts at 0 to infinity. This is c sub n, but that becomes c sub k plus 2. That n there is parentheses k plus 2. Then the n minus 1 is k plus 1 in parentheses times x to the k. It's minus 2 times the summation as k goes from, well, k is just n, so k goes from 1 to infinity of c sub k times x to the k. Okay. Math joke, but anyway. Doesn't work. My wife tells me, leave those stale jokes alone. Okay. So it's the summation as k is n goes from 0, so k goes from 0 to infinity, c sub k times x to the k is equal to 0. Well, I want to be able to factor out x to the k from all three summations, but I can't because they're all starting at different pivots. This is starting from k goes from 0. The second summation starting at k equal to 1. This guy starts at 0. So I need to evaluate the ones that start at k equal to 0, and then so I can have them all after that starting from k goes from 1 to infinity. So we're going to evaluate this guy. And then we'll evaluate this at k equal to 1. At k equal to 0, excuse me. So to do that, we plug in k to equal to 0. So that's going to give me, this is 2 times 1, so that's 2 times c sub 2, times x to the 0. And then I'll come over here and evaluate that second one, that third summation. So that's plus
c sub 0 times x to the 0. Now this is all plus now. The summation as k now is going from 1 to infinity because we evaluated the first and the last summation at k equal to 0. Now since they're all starting now at k equal to 1, I can go ahead now and factor out that x to the k. I have brackets, these terms here, so c sub k plus 2 times k plus 2 times k plus 1. I factored out that x to the k is right there in the front of the summation. Well, it's sitting not on the outside, but it's the inside. Then this is minus 2 times c sub k times that k, then plus, right here, plus c sub k. Close all that up. That's equal to 0. Well, if you look at it, this first term out in the front, this is 2 times c sub 2 plus c naught. X to the 0 is just 1. And that's plus the summation as k goes from 1 to infinity of x to the k times the brackets c sub k plus 2 times k plus 2 times k plus 1 minus 2 times c sub k times k plus c sub k. Close that up, equal to 0.
Now the whole thing is supposed to equal to 0, so that means that 2 times c sub 2 plus c naught has to equal to 0. So 2 times c sub 2 plus c naught has to equal to 0. That implies that c sub 2 is equal to negative c naught all over 2. So I'm going to just hold that over to the side. You know, when Granny is cooking and she has all her ingredients, some things she'll cook a little bit and get that ready, and she'll put it over to the side. It'll come back up, but she has to use it elsewhere. You know, when she's making tea cakes or banana pudding or something like that, she'll put certain things over to the side. So I'm going to put that over to the side. Look at that big summation. Well, for that guy to equal to 0, the terms inside the brackets must be equal to 0. So here, we say also c sub k plus 2. I'm just going to write what I have there in the brackets, set it equal to 0. C sub k plus 2 times parentheses k plus 2 times k plus 1 minus 2 times c sub k times k plus c sub k equal to 0. I'm going to solve for that c sub k plus 2, just solve for the biggest coefficient that I have, you know. So I wouldn't isolate c sub k because c sub k plus 2 would depend on c sub k. Right? So I'm going to write a recursive function. The recursion is on the c sub k plus 2 that depends or begs for the c sub k. So here I have c sub k plus 2, just do it like this first, plus k plus 2 times k plus 1, that's equal to, this is 2 times, so I just write it like this first, then I do my simplification. That's a k there, times k minus c sub k. I was going to do a division, but I'll keep it like that. This is 2 times c sub k times k minus c sub k, right? I just added 2 times c sub k times k to both sides, subtracted both sides by c sub k. Now I'm going to divide everything by k plus 2 parentheses times parentheses k plus 1. And that'll give me the c sub k plus 2 by itself. So this is c sub k
plus 2 is equal to, now this side over here is 2k minus 1. That's what I was going to write at first. All over k plus 2 times k plus 1, and that's times the c sub k. Just fracted out c sub k from that guy, and that's 2k minus 1, right? All times in c sub k. Well, this is our formula, our coefficient formula. So now, I'm going to let k equal to 0, solve for c sub k plus 2, let k equal to 1, k equal to 2, k equal to 3. Do that until I can see a pattern, right? So if we let k equal to 0, I get c sub 2 is equal to k equal to 0. That gives me a negative c sub 0, and that's all over. If k is equal to 0, that's just 2. But didn't we found that right here, right? That's the same thing, which is good because it lets us know that we're on the right track, right? See this guy right there? We found that. That was the ingredient that Granny set over to the side, right? So it comes back up, and it's going to help us because that ingredient is so important to everything else thereafter. Probably just may depend on it. Let's see. Now let k equal to 1. So I get c sub 1 plus 2. I get c sub 3 is equal to k is equal to 1. That's the formula. So this is 2 minus 1. I get 1 all over. K is equal to 1. So that's 3 times 2 times c sub 1. Let k equal to 2. So I get k sub 4 is equal to, plug in k equal to 2. That's 2 times 2 is 4 minus 1. I get 3. And then that's all over 4 times 3 times c sub 2. Let k equal to 3. So I get c sub 5 is equal to k equal to 3. That's 2 times 3 is 6 minus 1. I get 5 all over 5 times 4 times c sub 3. Let's just do one more. Hopefully that'll give us a pattern that we want. So c sub 6. So k equal to 4. That's 8 minus 1. I get 7 all over 6 times 5 times c sub 4. Now look at c sub 2. It's equal to negative c naught divided by 2. And we don't know what c naught is. Actually, when you don't know what c naught is, then typically that's being supplied by some initial condition. So basically the user has to input that value. Look at c sub 3. It's equal to 1 over 6 times c sub 1. I don't know what c sub 1 would be. So according to St. Thomas Aquinas, c sub naught and c sub 1 would be initial movers. Initial movers that we have no control of. Everything else depends on that movement. Right? So look at c sub 4. It calls up c sub 2. But c sub 2 is this guy up here. So this guy is, it's going to be that negative times that 3 all over this 4 times 3 times, there's a 2 there too, right? Times a 2, and that's times c naught. Now I'm leaving the 3 there because I can write this ultimately as negative 3 all over 4 factorial times c naught. Otherwise, it'll just be negative c naught all over 6. All over 8, excuse me, which is fine too. It's the same thing. Let's look at c sub 5. It calls up c sub 3. Well, c sub 3 depends on c sub 1. So this is, it's going to multiply 5 times 1. I get 5. And that's all over 5 times 4. Go back to c sub 3. That's in my denominator 3 times 2. And that's times c sub 1. I can write that as 5 all over 5 factorial.
Now, sometimes with the problems, you might not see a pattern. Like you might not see, okay, this guy is like factorials, or this is like 2 to the n. You might not see that. Well, just list them all out, you know? And that's fine, too. That's still the right answer. Make sure when you list them out that you've simplified it such that you get those initial terms in there. Like if they're dependent on C naught, you want to show that. If they're dependent on C sub 1, you want to go back. So in other words, I wouldn't leave C sub 4, I wouldn't leave this guy as 3 over 12 times C sub 2, or I wouldn't say C sub 4 is C sub 2 divided by 4. What's C sub 2? C sub 2 calls up, right? It's the initial recursion there of negative C naught divided by 2. So you got to show, you know, going back to the initial state. So C sub 6 calls up C sub 4. So C sub 4 is there. So this is 7, it's a negative there, excuse me, times a 3. That's all over 6 times 5 times 4 factorial. And that's times C naught. This is negative 21 all over 6 factorial times C naught. That's the definition for the factorials, right? 6 times 5 times 4 times 3 times 2 times 1. That's 6 factorial. Well, that's as far as I went, and that's fine. So now let's see if we can write the answer. That theorem says that if you're evaluating the solution about an ordinary point, you ought to have 2 solutions. So let's see if we get that. So you write your solution as always, y equal to C naught plus C sub 1 times x plus C sub 2 times x squared plus C sub 3 times x to the third plus and so on. So here y is equal to, and if you recall, C naught and C sub 1, they were the initial movers. Everything depends on them. So we don't know what they are, so we plug those in, plus C sub 1 times x. But C sub 2 called up C naught. C sub 2 called up C naught. Well, C sub 2 is negative C naught all over 2. So we put that negative C naught all over 2. That's times x squared. C sub 3 calls up the C sub 1. So this is plus C sub 1 all over, let's write that as 3 factorial times x to the third. C sub 4 is this guy right here. So this is negative 3 all over 4 factorial times C naught times x to the fourth, plus C sub 5 is 5 over 5 factorial times C sub 1 times x to the fifth. Then we had just one more there, minus 21 over 6 factorial times C naught times x to the sixth, that's C sub 6, plus and so on. And we can write our final answer. I'm going to group, get the C naughts together, get the C sub 1s together. That's the only good thing about using technology, right? Couldn't do that with the chalkboard. But with the chalkboard, I just leave it over in the corner somewhere and just, you know, circle it or something. So here, y is equal to C naught. I'm going to group it, get all the C naughts together. This is 1 minus x squared over 2 minus 3 over 4 factorial times x to the 4 minus 21 over 6 factorial times x to the 6. Looks like they're all minuses, so minus and so on. Close that up. Then plus c sub 1 here times x. And the next one is plus x to the third over 3 factorial, plus the next c sub 1 is the 5 over 5 factorial times x to the 5th, and plus, and so on. So these becomes our two solutions. Any questions there? A bit long, so just take your time with it. Well, I think that problem, it justifies that section. Only gave 3 problems there to do for homework. That's the one right there in the middle. I only have one major problem to do now, and that's the problem from section 6.3. 6.3 works on this, but it adds one more detail. Matter of fact, there must be a solution about a singular point. When they say the question about a singular point or about an ordinary point, it does not necessarily mean that I'm finding the solution at the singular point or at the ordinary point. It's the neighbor. Obviously, if it's a singular point, the functional differential equation does not exist. But about it in some type of epsilon neighborhood, then there may exist some type of solution. Remember that the solution is said to exist on some interval, the absolute value of x minus x sub naught is less than r. And that's what you did back in 6.1 when you looked for the interval of convergence, right? So the so-called differential equation is said to converge, that is, it has a solution in some type of interval. Right? So within that interval, we may be able to find a solution. So that's going to be 6.3. So let's look at that, and then we'll close out for today. Any questions here?